Council. I'd like to welcome you today to our latest in AEC's Tech Online webinars prepared exclusively for AEC members. Our session today in the series is Dye, Nitriding, and Dummy Blocks. Our presenters are Richard Dixon of Hydro and Paul Robbins of Castool Tooling Systems. Just of note, all computer audio and telephone lines are muted. So if you have a question during the webinar, type it in your Q&A option on your toolbar, and I will see that our presenters hear the questions at the end of the presentation, and if we have time, they will answer your questions. If not, questions can be answered in a follow-up process. You can either email me, Richard, or Paul directly. And now just a little bit about our presenters. Richard has been in the extrusion business for over 28 years, approximately 10 years with Alcan and 18 with Hydro. He's the Director of Customer Technical Support for Hydro Aluminum Metal Markets North America, after having served as Director of the Hydro Aluminum North America Technical Center for 7 years. He's been an active member of the AEC Dye Committee and serves on several Aluminum Association and ASTM technical committees. Richard is the editor and co-author of Hydro's Dye Design and Manufacturing Manuals. As leader of Hydro Aluminum's International Dye Team for many years, he drove the effort to create and refine ever more productive dye designs. Richard's passion remains advancing extrusion beyond its current limits through understanding and education. A little bit about Paul. The son of a leading Toronto dye maker, Paul Robbins was educated at Upper Canada College and York University. He received his postgraduate degree at the Schulich School of Business, and he's worked in the light metal extrusion industry for more than 25 years. Currently, he's general manager of Castool Tooling Systems, a Canadian company with the most complete line of world-class extrusion production tooling and equipment currently available. Robbins is well known as the author of the landmark 1996 article, Super Extruders, which introduced the theory that better extrusion depends primarily on measuring and controlling temperature at every step in the extrusion process. Paul holds several patents for improvements to extrusion technology that he's developed over the years. And he's been invited by organizations in a number of countries to present his concept of a systems approach to extrusion. And it's now being implemented by several of the world's largest extruders. And now it gives me great pleasure to welcome Richard and Paul.
Good afternoon, I'm Paul Robbins.
And good afternoon, this is Richard Dixon. Welcome to this webinar on dummy blocks and nitriding. But before we get going, we just need to make a plug that there'll be more on nitriding and a lot more on dye performance at the next Dye Performance Improvement Clinic offered by the AEC. This will be in October 27th and 28th in Indianapolis in Indiana. Also coming up is the AEC Maintenance Workshop. This is April 21st, 22nd in Atlanta, Georgia. Two really worthwhile clinics to go to, and I highly recommend them to you. If anyone wants to register for these, please just contact Lisa if you haven't already got details. So today, this is a two-part webinar. We're covering nitriding, basically the physics and chemistry of nitriding, and some of the implications this has on the quality of the nitriding you get. The second part, Paul will cover the way that a fixed dummy block works and how the fixed dummy block interacts with the other tooling so that we can understand this and better use the dummy blocks in our process. Now, we only have an hour here for two subjects, so we're not going to go in at tremendous depth, but we believe that we have covered all the key points in these two areas. And we are, of course, open to follow-up questions for people who would like some more information later.
We're also hoping to do a follow-up session on this at the management conference in September, where hopefully we can get into a bit more depth.
Yeah. So not all of you, of course, will be able to go to that meeting, but those that do, we'll cover what we can, and those that can't, just drop us an email or give us a phone call. So let's look at nitriding of steel. There's a lot of ways of nitriding steel out there. There's salt bath. Personally, I think for dyes, salt bath, which was what was used when I first started in the industry, was by far the best. It gave a great nitriding layer. It was easy to control. It was pretty forgiving to everything except the environment. I guess today having liquid cyanide around is considered a little environmentally unfriendly. So salt baths are basically becoming illegal in most countries now. So although it makes a great nitrided layer, I'm afraid it's being phased out worldwide. Then there's gas nitriding. This has some challenges with control. You have to balance the various gases in the system to get the right level of nitriding potential. But with the advent of computer controls, this has become a lot more common and a lot easier to control. Thirdly is ion beam or plasma nitriding. This is an absolutely excellent way of nitriding steel. The unfortunate thing with this is it tends to act like a point source. So whereas gas nitriding comes from all surfaces, the ion beam nitriding tends to give us a problem where it creates shadows. So if you're nitriding a thin-walled flat die, you'll end up with a shadow on one side or the other. So although the quality of the nitriding where you get it is absolutely superb, you don't get it everywhere. So really for dyes, it's far from ideal. For that reason, I'm going to focus primarily on gas nitriding, as this is becoming the industry standard. And I'm going to try and cover what's important to control in that process so that you get a good case depth and a good nitriding. First though, why do we nitride dyes? Well, we really want to increase the hardness of the bearings, and the purpose for that is to improve wear resistance. There is a picture here of a mandrel taken from a hollow tube die, and you can see my little cursor pointing. We have premature wear occurring here. This is known as washout by most die technicians. If we look at that washout under a microscope, here's the bearing length running from here through to here. The red arrow is pointing at this premature wear of the bearing. This gives you a poor surface finish on your extrusion, and as such leads to a reduction in the die life. Of course, any reduction in die life increases your cents per pound for your extrusion for your die cost. So this is a significant cost in our extrusion that we need to keep under control. What are we actually trying to make? Well, if we look at the picture on here, you're looking here at the surface of your steel. This is the outside edge of your die. This is the hardened layer we're trying to create, and this is the base layer of steel underneath. And these little marks you see, little squares, these are the indents from a Vickers micro hardness indenter, which is a square pyramid driven into the surface. And you can see the bigger the size of the dent, like here, the softer the steel is. The harder the steel, the smaller the dent we get. So you can see here at the very surface of this piece of die steel, it's very hard, and underneath it's a little softer. This is represented by these graphs. And you can see the best of these case thicknesses have a Vickers hardness at the surface of around 1,000, dropping to the bulk hardness of the steel, which is around 500 Vickers and equivalent to the mid-40s in Rockwell C. And the case depth is around the sort of 6 to 8 thousandths of an inch in depth. And that's what we're trying to achieve. In doing this, though, we want to be careful not to be over-enthusiastic. Here is another view of the surface of the tool steel. This is the very surface here. This is that layer, about 6 to 8 thou thick. Here is the soft steel, well, I'll say soft, the regular hardened steel underneath the layer, and there is this white layer on the surface, the compound layer. This is something we want to avoid. The compound or white layer is caused by being too aggressive in our nitriding, too hot, too high a nitriding potential, and we make a layer which is more like glass than it is hardened steel. And this can be a problem to us, and I'll cover this a little bit in a moment. If we take a close look, I flipped to the picture, sorry. If we take a close look at these little Vickers pyramid indenters that we put into a surface to look at the hardness of a surface. Here are two pictures courtesy of Nitrex, from one of Nitrex's publications. This left-hand picture is a pyramid indent which has been put into a good, hard piece of steel. You can see the pyramid is clearly defined and there is no cracking anywhere in the steel. On the right-hand side, you can see a surface which has been over-nitrided. In this case, there is this very, very hard, glassy layer in the surface known as the white layer or the compound layer. This has cracked, and you can see all these micro cracks coming out from the indenter. This is not good. This means that the surface is brittle and prone to damage. And on a larger scale, if we look at the surface of the steel, it can start looking like this. Now, surface cracks of this nature don't just come from over-nitriding and forming white layer. They can also come from impurities being on the surface. What do I mean by impurities? Anything from fingerprints, cutting oil, lubricants of various nature, spray dag. Quite often people handling dyes when they're putting them in the nitriding oven. If they don't think about it, they use the gloves that they normally use for handling dyes. And these are covered in various greases and lubricants from the extrusion plant. So these are transferred onto the surface of the dyes when they're put into the nitriding oven. The presence of these impurities or lubricants is a bad thing and leads to this form of surface cracking and also can lead to soft patches on the dye. This also brings up the question of preparing and cleaning the bearing. The bearing needs a light polishing with a relatively fine polishing medium, say 400 or 600 grit. There is not a requirement to remove large amounts of steel from the bearing at this time. And we have talked in other webinars about the importance of not over-polishing bearings. Remember, we are looking for cleanliness. We're not looking to remove large amounts of steel on the bearings. If we take over nitriding to its limits, we start to see this. This is the face of a flat face die, where people have tried to shorten the nitriding interval by making the nitriding parameters much more aggressive. And I will come back to the role of the different parameters and how they interact in getting a good nitriding layer. This problem with flaking is often made worse by the fact that people who use baff rings wish to remove this piece of aluminum from the baff ring somewhere in the die shop prior to putting it in caustic to try to save the amount of caustic used. If you remove that baff ring discard cold, the aluminum is sticking to the steel very, very firmly. And this can lead to making the flaking problems worse. Now you may look at this and say, hey, this is a piece of die steel away from the bearing, why am I worried if it's flaking? Well, I can assure you if one of those pieces of flakes gets pulled off the surface during extrusion and ends up going through the die, you will notice this in your product and it may actually have a permanent effect on the bearing. So it's good to avoid. So, there are two tricks to getting nitriding right. The first trick is to get nitrogen into the surface. because we have to get the nitrogen to penetrate into the dye to a depth of around about 6 to 8 thou. Now, molecular nitrogen, which is what's in our air, is a big molecule. It's 2 nitrogen atoms together, just like oxygen is O2, nitrogen is N2. So as we breathe, sitting listening to this presentation, I hope everyone is, we're taking in about 80% of our lungs take in nitrogen. It's a sizable molecule, and it's too big to easily diffuse into the surface of a piece of steel. We need to find a chemical way of breaking this nitrogen molecule down into nitrogen atoms, which are then much smaller and can much more easily diffuse into the steel. So that's the first trick in getting nitriding to work, is the creation of atomic nitrogen to diffuse into the steel. The second trick is, once we've got that atomic nitrogen, is using it in the right way, getting the right amount of nitrogen and at the right temperature. As Paul has said in his super extruder paper all those years ago, everything is about temperature. Well, guess what? Nitriding is also about temperature. So we need the right amount of nitrogen in the right place at the right temperature. Too much or too little, we end up with it being either brittle, as you saw in those pictures of it cracking and flaking, or we don't make the dye hard enough and we've just been wasting our time. So we really need to get the balance right in the amount of nitrogen and the temperature at which we get that nitrogen into the surface of the steel. To get the nitrogen in the atomic form in modern ammonia-based gas nitriding, we first need the right mix of gases coming into the reactor. Now, this can be a little complicated. There are different methods out there. There are people that do this at some pressure, some do it at low pressure. There are different techniques, but the fundamental physics and chemistry remains the same. We put in the gases, and a reaction occurs in combination with the steel surface. Now, this is perhaps, if there is only one thing you remember from this presentation later on in the week, this is the key element. The steel surface is an important part of the reacting of the ammonia and the gases together to give us the atomic nitrogen. I have to ask you, what happens, oops, I lost the slide there. What happens if this surface is dirty? The steel isn't available to us. Let's look at the reaction. Please don't get put off by this. It's not as complicated as it looks. The first part here in the red circle says that all we're doing is we're taking ammonia, which is in the general nitriding atmosphere, and it diffuses naturally in air, so there is some ammonia in contact with the steel surface. The next part is the reduction of that ammonia. That's a chemical reaction which turns ammonia, which is nitrogen and hydrogen. Basically, at the correct temperature and the correct conditions, it creates atomic nitrogen and atomic hydrogen. Some of this recombines back into molecular nitrogen and hydrogen and simply returns to the nitriding atmosphere. This is a little bit of a waste because we don't get anything out of it. But some of the atomic nitrogen and hydrogen diffuses into the surface of the steel. The hydrogen, it's really not that significant in this process. Most of it combines to make H2, and at some point diffuses back out of the steel and we lose it. So it's not something we should really concern ourselves with. However, the nitrogen goes on to react with the steel. Some of the nitrogen is trapped by the iron, and that's this reaction we see over here to the right. We react iron and nitrogen together to make an iron nitride. Some of the nitrogen is just dissolved in the steel. It doesn't react with anything. And some of the nitrogen reacts with chromium, aluminium, molybdenum, and other other alloying elements in our steel. Now this can get very interesting because now we start talking about what alloying elements we need to get the best nitriding response. I can tell you I did some tests in the late 90s with some steel from Bowler, and it had aluminium in it. It was killed with 0.5% or 1% aluminium in the steel. It nitrided as hard as I've ever seen anything nitride. However, as with the white layer, it was too hard, and it gave us a lot of problems with cracking and flaking. Now I understand there are better steels around now with a little aluminum in them that can get over this problem. But generally, H13 is pretty good at this. It has a little bit of all the good stuff in it, and the nitrogen reacts with this and is trapped in the surface. So that's the three places our nitrogen goes. Now, as I said, note that the chemical activity all occurs at the gas-steel interface. What happens if there's a layer of grease and dirt on this surface? The reaction doesn't happen. Atomic nitrogen doesn't exist in the gas form in the reactor. Any atomic nitrogen which comes off the surface immediately reacts with another nitrogen atom and forms a nitrogen molecule. So there is no mechanism for atomic nitrogen to go away from where it is formed. Thus, if you have grease, a fingerprint, dirt, dag, or something on the surface, no atomic nitrogen will be formed there, and no nitrogen will go into the surface. So you will not nitride the dye where it is dirty. Additionally, the amount of steel in there is important. So don't run your gas nitrider with just one dye in it. You should run it at a full load every time. Now, what I used to do was I used to keep some spare dyes which were worn out or had the end of their life, which we used to balance the load in the gas nitriding oven, so we had all the steel needed to cause these reactions to occur. Please, these may be scrap pieces of steel you're using, but they need to be just as clean as everything else which is in the reactor. So that's creating the nitrogen. And I hope the message I've got across to you here is that cleanliness is next to godliness in nitriding. If the surface is not clean and available for the gas to make contact, you will not form atomic nitrogen and you will not nitride it. Once we've created the nitrogen, the next trick is to use it in the right way. And this is about time and temperature. We need the right amount of nitrogen in the right place at the right temperature. Now, here is a really quite technical diagram which relates the temperature of our nitrider, which is this up and down axis, and I've put real units in red, and we've got the non-standard units used in the rest of the world for the Canadians and any South Africans who are watching. But for people using real units, here they are. And across this way, we have the nitriding potential. This is the mixture of ammonia in our gas. It's how aggressively we are trying to nitride. So, if we operate around about 800 Fahrenheit with a low nitriding potential, we form a phase called alpha. It's just plain soft. We're wasting our time. If we nitride at the same gas potential, but at 1400 degrees Fahrenheit, it's too hot for the steel. The tempering temperature of H13 is around about 1000 degrees Fahrenheit, maybe 1100 degrees Fahrenheit. 1085, Paul is telling me is the exact number. So if we go all the way up here to 1400, we're going to soften our steel. So as we turn up the nitriding potential, we now move into a range here, which is this gamma prime. This is what we want. If we make gamma prime down here with high nitriding potential but at low temperatures, we will make a great nitriding layer, but it will take us until next month to achieve it. So we need to go hotter to speed things up. If we, however, go too hot, we go into this epsilon range. This is the white layer. This is the brittle layer we do not want to create. So we have this red circle. This is our optimum range that we want to work in. And if we look at it in terms of the ammonia content or the nitriding potential content here, we have a green range to operate in. And if we look at temperatures, we have a green range to operate in. I'm now adding in a line, which is the tempering temperature of H13. If we start to go above this, we start to soften our dyes. Not dramatically at first, but over many, many nitriding cycles, it could become an issue. So really, this lower part here, if I can get my mouse to appear on the screen, here we go. This lower part here is an ideal area for us to operate in. This gives us the good nitriding layer. It does not give us the white layer, and it does it at optimum nitriding speeds. There are systems out there. The one I'm most familiar with comes from Nitrex. This is computer controls to achieve this. I have seen older style nitriding machines where you have to sit there and do the calculations of your nitriding potential and adjust gas flow. I find that to be a little challenging even myself. So for someone on the night shift, I think that could be a little bit too challenging to get a good quality finish. Let us look at what we make. This is the hardness values measured going into the steel. And this first line here is the very first nitriding cycle. Note that as we increase to 3 cycles and 5 cycles of nitriding, the free nitrogen, which is in our steel here, can migrate both ways, and it goes inwards. So this nitrogen we have in here is going to be the nitrogen which gives us the good case depth after 3 or 5 cycles. Now, people often ask me, how often should I nitride a dye? Well, obviously you need to nitride it at the beginning, but what you get is this first nitriding layer. And this is actually quite a fine, delicate layer. So our first period before we do our next nitriding should be relatively short. And as we get on towards 3 to 5 layers, we can extend out our period between nitriding cycles. The other thing is, it's always been my approach that I don't take a given number of billets between nitridings. I take a given distance, be it in feet, meters, miles, or whatever you want, of extruded product. Because if you're making a 1-inch round bar, you extrude very little round bar for quite a few billets. Whereas if you're making a 40 thou thick small glazing clip for windows, you extrude an enormous distance of material running at speed over the bearings. So I always use distance as the guide to my nitriding cycles. Let's look a little at what happens when we put a new dye with just one nitriding cycle into our dye ovens. The blue line shows you the hardness profile of this dye prior to going in the dye oven. If we leave the dye in the dye oven for 24 hours, the red line is now the hardness profile of the surface of the dye. And you can see we might as well have not bothered nitriding it. All the good stuff, all the stuff we have worked so hard to make right here is lost. The nitrogen simply diffuses at the preheating temperature out of the surface. So a key part of good nitriding is also good dye preheating. So the bigger the dye gets, the bigger this problem gets because it takes longer to heat it up. And once you pass about an 8-inch dye towards a 9-inch dye, you really do need to start seriously considering heating dyes one at a time. Now, some people say putting nitrogen, which is N2 gas, into the dye oven makes all this problem go away. I wish it was that simple. The problem we have is that what is diffusing out of the steel is atomic nitrogen. The second that atomic nitrogen is free of the steel surface, it reacts to make molecular nitrogen, and it's gone. Molecular nitrogen does not diffuse into steel. So although there is a minor effect of having nitrogen in the dye oven to protect the layer, and this is mainly because it eliminates oxygen from the surface as a reactant, it really doesn't totally prevent the loss of nitriding in the dye ovens. So you want something that heats the dye up quickly and then use the dye. I'm willing to challenge you and say that probably 50% of the people listening today, if you went out to your press, would find that you have had a dye in an oven for 24 hours at some point over this week. So let's not consider this as a minor problem. This does have a big impact on nitriding. So, summary for nitriding. Clean dyes. One of the things I believe in, and I've always done when I've worked in a plant, I make the people loading the dyes into the nitriding ovens wear white cloth gloves. If they can't keep their white cloth gloves beautifully clean loading the dyes, then the dyes are not clean enough. You need to work on that. You need the correct volume of steel in the reactor. No half loads, no part loads. Have some steel to top it up. Get your gas mix right. Get your dissociation mix right. Operate at the correct temperature for the correct time. And of course, you always hear from me, trust but verify. What I believe is that at least once a month, probably more frequently, you should run a test block in your nitrider and send for testing. Sorry, there's an S missing there. That should be send for testing, not end for testing. What you do is you contact your dye maker and say, please give me a piece of H13 about 1 inch by 1 inch by half an inch, and you put it in with the dyes. It gets nitrided and you send it to a lab. You should be able to get a simple lab report with a picture of the nitrided layer telling you if there is a white layer formed, how thick the case depth is, and a few provisional hardness levels, just to tell you everything's right. Should cost about $200. If you don't have a local lab that can help you out, I'm sure that the Hydrotechnology Center would be happy to assist by doing these tests in exchange for some money. This is a service that Hydro is happy to offer to the industry if you need it. And if you do, contact me after this webinar and I'll put you in touch with the guy that runs the lab and you can talk to him about your needs. But regular testing that things is working is important. Just imagine in your head the value of the dyes you have in your nitriding oven every time you run it. And a nozzle or a jet has got blocked somewhere and you're not feeding ammonia in. You are not hardening your dyes. Your dyes are running at the press and the bearings wash out. This will dramatically increase your cost in cents per pound for your dyes on your product. So a simple test once a week, once a fortnight, or absolute minimum once a month is something you want to do to make sure everything else is working. So that's me going through nitriding. Sorry, I've run over by 3 minutes. I apologize to Paul. I pass to Paul, who's now going to talk to you for dummy blocks, and I'll take questions at the end.
Where's the microphone? Here? Oh, okay, good. Well, good afternoon again, and welcome to part 2, or dummy blocks. It's one of my favorite slides, and it's pretty simple. Extrusion is deceptively simple. A hot billet is inserted into one end of the liner and pushed out the other. And we want to do this repeatedly and as quickly as possible. But unfortunately, to do it with low recovery and to make money, it's not quite this simple. The dummy block is a critical element of the production system, and it affects both quality and productivity. By this, it can affect your surface finish, It can affect your porosity or the amount of blisters in your profile, and by all means your cycle time and downtime. We started out with a loose or floating dummy block prior to 1986, and I must admit I was in a country back about 2 months ago where 95% of all the extruders still use loose or floating dummy blocks. The problem with these dummy blocks is, number one, most of them spend some time on the floor or in the pit and they're dirty. Most of them fall into that pit and they become irregular or damaged. They typically extend the dead cycle because we have to load them and unload them every cycle. They cause unscheduled downtime because often the dummy block isn't put in front of the stem and you actually push the ram into a hot billet. They typically limit the billet length that we can use in a container. When we use a fixed dummy block, we can use a longer billet for each extrusion. It also becomes extremely difficult or maybe impossible to have a burp cycle. With a burp cycle with a fixed dummy block, we hope that it will relax and be reduced in diameter during the burp. And with a fixed or a loose dummy block, this is impossible. An effective fixed dummy block needs to do several things. We want to repeatedly transmit the force of the ram to the billet. Number two, it needs to expand quickly under load. In most cases, we're looking at our dummy block to mechanically expand about 30 thou in diameter. We want it to maintain a secure seal with the container so that no aluminum passes by. And we would like to leave a uniform thin film of alloy somewhere around 8 to 12 thousandths thick on the ID of the liner. We would like the rate of expansion of the dummy block to equal the upset rate of the billet, in which case we can eliminate any of the gas entrapment between the billet and the liner. We also need the dummy block to separate from the billet at the end of the stroke so we don't cause any downtime discarding the butt. Prior to the dummy block coming back through the liner, it needs to contract immediately back to its original size and come back through the container without stripping any of aluminum from the ID of the liner. If we dissect the dummy block, we have a few components. We have a mandrel, which we use to actually push back into a ringer flange to expand the dummy block. We have a pad area that supports the mandrel when it's pushed back, and we have a coupling that attaches the fixed dummy block to the stem. We also have an angle between the mandrel and the flange or the ring. These angles are anywhere from a minimum of about 20 degrees to a maximum of 35 degrees. And typically we have anywhere from half a degree to 1 degree difference between the angle on the ringer flange and the mandrel. We also have a gap between the back of the mandrel and the pad area, and it's the movement of the mandrel within this gap and the amount and steepness of the angle that give us our expansion. Basically, the mechanism is like this. We have a mandrel that's moving somewhere between 20 to 35 thousandths of an inch. We have an angle between 20 to 35 degrees, and our goal is to expand the ring somewhere between 30 to 40 thousandths of an inch on diameter. These are just a couple examples. Often we use a 25-degree angle between on the conical component of the mandrel and the ring, in which case we would have about a 40 thou gap between the back of the mandrel and the pad area, which would give us 37 thousandths of an inch on diameter expansion. If we take the same dummy block and we use a 30-degree angle, the gap would be reduced to about 30 thou, which would limit us to about 35 thousandths of an inch expansion on diameter. And again, this is just mechanical and does not include thermal. The goal when the dummy block is expanded is to leave a skin thickness of somewhere between 8 to 12 thousandths of an inch. And ideally, we would like this to be uniform thickness all around the ID of the liner. What we do know today is if that gap becomes greater than about 20 thou, there's a risk of extruding metal back past the dummy block. So for some reason, if the dummy block doesn't expand enough, or if the liner is actually bigger than what we're expected to be, this is when we have aluminum coming back behind the lip of the dummy block and causing premature sealing in the future. The rate of expansion also matters. If we expand too fast, the dummy block will actually pre-seal on the liner, and the air entrapment between the billet and the liner then will not get out, and we'll have a series of blisters. If the dummy block expands too slow, then it's possible that we could actually extrude by the dummy block prior to billet completely upsetting. What we know is that to crush a billet takes about 100 tons of pressure. So this number gives us a way of looking at the rate of expansion between the angles. And typically, if you go back, we started doing fixed dummy blocks in 1986. If we go back 29 years, we were using angles of about 20 degrees, and your standard press then was about 80,000 psi. Today, the majority of presses are between 90 to 100,000 psi, and the angles are typically anywhere between 25 to 35 degrees today. So we've adjusted our rate of expansion over the last 30 years. The pad area is also very, very important. As the pad area changes or becomes deformed, it changes the amount of expansion in our dummy block. So if we go back a couple of slides and we take a look at a 25-degree angle, we would have a 40 thou gap between the back of the mandrel and the pad area. But if the pad area is under too much pressure and actually is moved or deformed by 10 thou, at that point our gap will be increased to 50 thou and our expansion will go over 40 thou, which means that the dummy block will be prematurely sealing on the liner and we can't get rid of the gas entrapment. So the calculation of the pad area on the dummy block for every given press becomes extremely important. And it's something that should be monitored, especially on dummy blocks where you have reusable components, so that we don't allow it to be deformed. This is a graph I've been using for many years, and every dummy block has deformation. If we make a dummy block at a given size, after the first couple of pushes, it will deform permanently somewhere between 4 to 8 thousandths of an inch on diameter. What we hope to do when we manufacture dummy blocks is to limit the amount of deformation for the longest amount of time. A poor dummy block will start deforming very, very quickly. So if a dummy block started at maybe 8.360, and after you use it for a day, it's 8.370, we've seen about 10 thou deformation. If we see 20 thousandths of an inch deformation, so the original size is increased by 20 thou, we're going to start prematurely sealing we're going to start interfering with that aluminum that we left on the ID of the liner, and we're going to see an increase in blisters and our surface finish decrease. So again, what we want to do is extend the life of the dummy block and limit the amount of permanent deformation for as long as possible. If you have a dummy block that's giving you problems, what you should do is take it off the press, let it return to room temperature, and measure the outside diameter on your X and Y axis, and go back to the person that manufactured it and give them these numbers and resolve why it is deformed prematurely. There are several ways of putting dummy blocks onto stems. The majority of us 30 years ago were using double-end threaded studs. The problem with these, if the dummy block loosened from the stem and the threaded stud took the amount of pressure that was put onto the face of the dummy blocks, we would get deformed threads, in which case it would be very, very difficult to remove the dummy block. What we started doing next was attaching the dummy block to a threaded rod which went through the stem. The rods in most cases floated, so this prevented us from putting excess pressure on the threads. The problem with both of these is we want to make sure the dummy block, when it's used, is about billet temperature. And if we're threading a dummy block that we hope is about 800 degrees onto a threaded stud or rod, it's going to be extremely uncomfortable for the person installing the dummy block. There's several of us that started using bayonet studs, and one of the main reasons to use a bayonet stud, so it was easy to put a hot dummy block onto a hot stem. I talked quickly about rate of expansion of the dummy block. The other half of rate of expansion is what the billet actually looks like. If we take a thermal profile of the billet, we would hope that the back of the billet was colder than the front of the billet. As we know from many of the talks we've had before, is flow stress is increased when the billet becomes cooler. So if we have a billet that's tapered so it's hotter at the die end than the dummy block ends, we can get a consistent or a progressive rate of upset, in which case the air is pushed to the back where the dummy block is, and the dummy block then, if it's working correctly, will enable us to evacuate the air. Unfortunately, many of the old billet ovens give us a reverse taper, in which case the die end of the billet is actually cooler than the dummy block end of the billet. In these cases, we actually get a reversed upset, so the billet will actually start to deform or crush at the dummy block side towards the die end. Unfortunately, the dummy block can't help with this type of a blister, and the only way we can get rid of this air is through the burp cycle. I was actually at an extruder 2 weeks ago, and I hadn't seen this before, that we're heating their billet sideways. So they were heating it from the front and the back end of the billet. And in all cases, the center of the billet was cold. When we have this problem, we're actually going to start crushing from both ends and to trap gas in the middle. Again, the dummy block can only help you with gas that's at the back end of the billet. The rest of it is also all process management. Today, with 6000 series billets, what we're seeing in general is about 5 degrees Fahrenheit per inch taper is required to be a super extruder. I'll go back to my old word. There are some extruders globally that are using as much as 10 degrees Fahrenheit per inch. I think this is pretty aggressive, but Richard?
Oh, it's aggressive.
But 5 degrees Fahrenheit per inch would be probably an acceptable.
About 100 degrees centigrade per meter.
Okay.
So yes.
Very good. Thank you. The dummy block also interacts with the container. Unfortunately, it doesn't operate in isolation. The successful operation, we need a press that's aligned, both thermally and physically. We need proper lubrication between the dummy block and the billet, also internally within the dummy block. But the most important thing that we require is a round and straight container. It needs to be thermally and therefore dimensionally stable. And stable is a word that you hear me say quite a bit, and the only way that we can have reliability is for the temperature and size to be stable every cycle and every day. There's also some mechanical features to the containers. And today we're seeing containers up to about 60 inches in length. The challenges with longer containers, if we take an 8-inch container that's 40 inches long and a standard 2-piece container, we get about 34 thou expansion under pressure in the center of the liner. If we take that same geometry, same container, and make it 60 inches long, the ID of the liner will expand 51 thousandths of an inch. The problem is, and we've said it prior, that if the gap between the dummy block and the liner becomes greater than 20 thousandths of an inch, we will extrude by the dummy block. So in these longer containers, we need to do something. The easiest way to cope with this is, even at the same pressure, is to go to a 3-piece container versus a 2-piece container when we start using containers much over 40 inches in length. We can decrease the amount of expansion in the container by about 35% by doing this. So we can make a 60-inch container act the same as a 40-inch container for the same billet size and same pressure. The other part of the container is thermal. And we know that when tool steel expands, when tool steel is heated, it expands. And steel expands 0.000011 millimeter per millimeter per degree Celsius. So if we take our same 8-inch container that we just looked at, it would expand about 37 thousandths of an inch at 830 degrees. The good news is the dummy block should be about the same temperature as the liner. And as long as the dummy block is the same temperature as the liner, the thermal stability or temperatures don't have much effect. Where this becomes a problem is we have many containers that can be 50 to 100 degrees on the top than the bottom, in which case we no longer have a round and cylindrical liner, we have ovality. In these cases, you'll see blow-by or extruding by on the top and possibly the bottom of the dummy block. Cleanout blocks also should be used for various reasons. We look at using a cleanout block at least one time per day for press maintenance, and also any time that we do an alloy change. What we want to use it for the dummy block is so we can take a look at our alignment between the dummy block and the container. And we'd like to use this at least one time per day. When we run the cleanout block, if we see a crown on the front of the cleanout block, it's a sign that we have very good alignment between the stem and the container. If we see a tiara on the front of the cleanout block, it says their alignment is out in the direction of the tiara. Very simple. And if this is done every morning at 8 o'clock, we have a quick and simple way of checking our alignment. Lubrication of dummy blocks, there's basically two key areas. We have the lubricant, or I prefer to call it the release agent, that's put either on the face of the mandrel or the back of the dummy block. And this can be either acetylene soot or boron nitride. And the boron nitride can either be applied as a liquid or as a powder. We also recommend at least one time per week taking the dummy block off the press, cleaning it thoroughly, and either putting high pressure grease or boron nitride powder or liquid on the pressure area between the angle on the mandrel and the angle on the ring or flange of the dummy block. For billet release, this can be done, as I mentioned, either with powder or liquid. And I think the market is tending to go more towards liquid these days. Acetylene soot also works, but again, there's some environmental problems with it. Thank you very much. That ends my session on dummy blocks.
We're just about on time here, Lisa, so you don't have to chase us down and beat us later for being too long.
Perfect timing. Thank you both so much. That was a terrific presentation. We do have some questions that have come in already, so I would like to go ahead and start with and dig right into those. First one is, how many times should dyes be nitrided?
How long is a piece of string? Let me say that the minimum to me is 5 times. That's when you establish a good, stable layer. The case depth then is good. It's around 6 to 8 thou, provided, of course, you haven't left the dyes in the oven for a fortnight. Once you've built up that good, stable layer, you really just need to top it up occasionally. You lose a certain amount of nitrogen from the very surface. But once you have that good, solid case depth, you can go out to much longer nitriding intervals. One thing I think is really important, and I'm glad you brought this up, whoever questioned, because I forgot to mention in the presentation. One thing with hollow dyes, if your mandrels have started cracking, stop nitriding the mandrels. The nitrogen goes down the crack and embrittles the tip of the crack and encourages the growth rate of that crack. The likelihood is that once your mandrels have started cracking, the wear of your mandrel is not an issue. It's going to be the mandrel will fail by cracking. So we strongly recommend that once a hollow bridge part of the dye has started cracking, significantly reduce or eliminate further nitriding. I have seen some dyes, however, go on for some considerable period of time with cracks in them. In fact, I've seen some go to the point that it actually quite worried me how cracked they were and still function. So dyes can go on a long time after they've cracked, but nitriding them will reduce that amount of time. So I would say the best answer I can give to that is I would say 5 nitridings is probably the minimum over the life of a dye, but stop once you have cracks in mandrels. Dye plates, if you get a crack in the dye plates, then also stop.
Okay, next question. If we want more nitriding layer, what is the procedure for this? Usually we nitride 0.002 to 0.004. We have nitrix furnace.
Well, the thing is that the very first nitriding, whatever you do, it's not going to go very deep. So this is where you really want, you do your first nitriding, you run some production. You want to bring that dye back for nitriding at a relatively short interval. And as I say, measure distance of extrudate rather than weight or a number of billets. Then once you've done your second nitriding, you're starting to get a better case depth. So as you go 1, 2, 3, 4, you can start increasing the period between nitrides. I've done some tests way back in my past where we started looking at trying to put a really heavy nitride in on the first time, so that as a dye maker, which I was working for Hydro's Dye Shop in France, we were trying to produce a dye that was already had 5 nitriding, so it was perfect for the extruder. This didn't work at all well. We ended up with making white layer. We ended up getting all sorts of problems with it. It does seem that nitriding needs to be progressive. and in some ways gently progressive. So you just have to accept that your first 1, 2, 3 nitrides are developing this ideal layer. I don't think it's really very easy without salt baths to jump directly to a good deep layer.
Okay, we've got several questions. I hope everyone's all right with going a little bit long today. The next one is, what is the reason of nitriding flaking?
Flaking, I think, has mixed sources. I suffered a lot of flaking in my last plant in the UK. And this was being made worse by the fact we were using bafferings. So every die, when it arrived in the die shop, had a 1-inch deep, 7-inch diameter block of aluminum stuck to the face of the die. This was on an 8-inch press. And we didn't really want to stuck all these blocks into caustic, so we used a cold shear to knock these blocks off the surface. This stressed the over-nitrided layers in the surface of the die and led to some flaking. Now, as I said, flaking isn't the end of the world, but if a piece of that flaked steel becomes loose and doesn't come actually free until it's in extrusion process, it will spoil your day for the quality of surface. The next thing is, quite often, simple over-nitriding. People are trying to be a little over-aggressive in the amount of nitriding they do to reduce the number of cycles. There are limits. They should be challenged, but they shouldn't be broken. And the last thing which causes flaking, and I think is probably the most common, is good old-fashioned dirt and grease being on the surface of the die, interrupting the way the process works. And cleanliness really is next to godliness in nitriding.
Okay, next question. If the surface needs to be cleaned prior to nitriding, what should be used?
Okay, I will answer this question 2 ways. The first one is, there is no if in this statement. The surface needs to be cleaned prior to nitriding. Some people use aquablasting. I know there are several systems out there that do this light blasting with water. That can be quite good. I personally like having the surface wiped down with an organic solvent. I like ethanol, but it depends on your choice of organic solvent. That removes a lot of things. The bearings, of course, should be cleaned with a 600 or 400 grit, maybe even 1,000 grit paper. We have to remember that usually prior to nitriding, the dyes have come from caustic. And there are some residues from caustic that really need to be removed. This comes also into the question, how long do you leave a dye between coming from caustic and grit blasting after caustic before it goes into nitriding? If you leave the dye laying around for a long time, it can accumulate dirt and grease from the atmosphere plus corrosion. Oxides on the surface are not good things to have with regard to this reaction that turns ammonia into atomic nitrogen and hydrogen. You really need a clean steel surface. So corrosion should be treated as dirt. So I would say aquablasting or regular grit blasting, but please be tempted not to turn the air pressure up too high. It can do some damage to the bearing entrance and exits. So aquablast, and then maybe some alcohol and a clean cloth. But I think the neatest trick is just to get your guys that load the nitriding ovens to wear white cloth gloves. And that's a good test of how clean the dyes are when they go in.
The next question is very similar, so perhaps it was addressed. But the next question is, do you have any suggestions for good cleaning solutions for final pass before going into the nitride?
I like alcohol, but I'm afraid that comes back to my student days.
Okay, the next question. Can you re-nitride dyes too soon, and will this damage the dye?
I have no direct knowledge of that. We were going to do some tests when we were doing those, trying to nitride the dye perfectly the first time by just putting the dye back round again. So I have to say on that one, that's a very good question, and I'd like to know the answer myself. So If there are guys out there that have done this, I'd like to know. That'd be useful.
Next question. Dyes are brought in nitrided when new. Is this a good practice?
Well, this comes down to what we call the dye trial rate of your dye manufacturer. And this comes back to paper that Hydro put forward to ET at 08 about having a specification with your dye maker and telling your dye maker what your expectations are. I like the idea of dyes coming in nitrided from the dye maker, provided that I have a very high percentage first run on those dyes. My dye correctors would much rather try to correct bearings on a dye which is not nitrided. If you come into a nitrided dye, it's a lot harder to work on.
We're back to temperature management. If you manage your temperatures, you're going to reduce the amount of dye correction, in which case can lead to having dyes that are pre-nitrided.
And you need stable process at your end and stable process at the dye maker's end. I have seen plants, Rockledge in Florida, which now is the Sapa plant, at one stage had a 97% zero dye trial rate. So 97% of the dyes that arrived ran first time. And so they were very confident to have their dyes come in nitrided, and that saved them a process step in the plant. If you don't have that confidence, then of course it's a very different matter.
Okay, sometimes explosions may happen during burp cycles. What is responsible for those explosions?
Chris Jowett actually put a very good paper into ET12, I think, on this. Is it ET8? Yeah. I'll have to look it up. But Alcan did some very good work on this, and they actually videoed some explosions and made them better and worse. Entrapped air is definitely a major part. And entrapped air under pressure is a big thing. But what actually turns it into an explosion is the presence of something which can combust. This normally has to be carbon-based and is usually an oil. So if you have a clean press, you don't get nearly so many big bangs, you just get a release of gas.
And the better extruders today don't allow graphite or oil substances close to the press.
But those oils in the press mixed with pressurized air do make very impressive and quite scary noises. Also, if you look at the front of the container and the dye afterwards, there is gas cutting. If you get frequent explosions, there will be quite severe damage done to the dyes, the dye rings, and the front of the container. So when you start getting these things, you really do want to start getting a procedure of making sure you have the correct temperature profile on your billet so that the upset does not trap gas. And you want to make sure there is nothing combustible to react with that gas to give you the explosion.
And I would say typically if we're getting explosions at the front end of the container, we typically have a seal face that's too big, which means that we're getting mushrooms or sombreros. Then we're putting grease on that surface.
Yes.
Typically then we also have a butt shear that's not working very well, and we're putting grease on the butt shear. And in many of these cases, we have a reverse taper on the billet because the older log furnaces or billet furnaces actually deliver a reverse taper on the billet. So we're basically making a gun. We're making sure we have compressed air and oil at the dye end of every container.
And Paul makes a very good point that I hadn't thought of it, but the shear is an important element in this. If the shear makes a smooth, flat, uniform cut every time, and a smooth, flat, uniform billet is presented to it, and there is no oil present, it's very, very difficult to get explosions. If you have a shear which pulls metal out from the die, and in response to this your crew covers the blade in some form of lubricant to try to reduce this problem, then you are beginning to get yourself into a vicious circle, which will end up with explosions, damage to equipment. And remember, that which damages steel is capable of damaging the people if they're too close to that area.
And typically, if the butt shear isn't working, the seal face on the container is too large, and we're getting blow-by. They all seem to go together.
Richard and Paul, we still have 7 more questions. Do you want to keep going, or do you prefer to answer these in the?
Well, Paul has to go. Paul has to go to the airport.
Okay.
In a very near time. He probably has a couple of minutes, but I'll stay and answer questions as long as necessary to cover for him.
Okay. Well, then we'll keep going.
Thank you very much.
Thank you, Paul. Is there any cold dummy block design that would work with an UBE loader conveyor?
Go that one again, Lisa, because Paul's got to answer that one.
Is there any cold dummy block design that would work with an
cold
UBE
clean-out
loader?
Block. Send us some notes afterwards, and we'll work with you on it.
Yeah, the use of front-loading presses and clean-out blocks is an area which is challenging. And last webinar, a month ago, we actually mentioned the UBE method, where it has a loader and it drops a clean-out block down. Yes, there is a cold design that can be used with that, but it would need some development.
Talk to us later.
Thank you, Paul. Next question. How many billets run through the die should you re-nitride?
That's a good question. Again, I say I don't go for number of billets, I go for distance.
Extrusion ratio.
Your extrusion ratio is important. I mean, if you're extruding something which is less than a pound per foot, as opposed to something which is like 10 pounds per foot, the amount of bearing, wear, and usage is going to be quite different. So first of all, I go for distance rather than for number of billets or weight. Exact distances I can't give you because the numbers I have only come from one company and they don't like me sharing that information. But I will look and see if I can find something. If whoever sends that question in would like to email me, I will try to find if I have information I can share with you without breaking any confidentialities I have with extruders.
Okay, Richard, you made the comment that you read nitride after a certain number of linear feet instead of number of billets. What is the approximate number of linear feet?
That's referred to previous answer. I can't say that. But I have various rules, and I don't claim them to be perfect, but I limit the number of billets a die will do at any one visit to the press. I limit the number of billets a die will do prior to nitriding. And this requires a certain amount of effort to track them. If you overrun your nitriding interval, yes, you may help yourself out on that one occasion, but you will probably damage the die for the long term. A well-nitrided, well-prepared, well-looked-after die will last a long time. And I have very, very few hollow dies I've ever worked with where the bearing wear has been the issue. It's normally webs cracking and webs pushing in. So if you do it right, it's very good. And I will also, if that person would like to contact me later, I will try to get some numbers that I can give the number of linear feet for extrusion prior to nitriding.
Okay, the next question looks to be fairly similar. Is there a rule of thumb for re-nitriding based on a lineal feet produced in a die?
Yeah, basically it's between 1 and 2, 2 and 3, 3 and 4, and 4 and 5. You can increase the amount of extrusion you get. Once you get to 5, then I consider the die is out there for good long productions. Again, I can't give an exact number because I'm bound by some confidentiality in that, but I will look and see if there is anything published in ET because I can pass that around.
Okay, I think the next question you've addressed pretty well, but the next question is how to clean a die before nitriding.
Yeah, clean the bearing with 1,600 to 600 grit paper, light pressure, polishing at 90 degrees to the extrusion direction, aqua blast or light grit blast. If you light grit blast, make sure you remove any grit that becomes embedded in the surface or is around, and then finish off with some form of mild organic solvent such as ethanol or acetone to remove any organic material. Once you've done that, do not then allow the dye to go somewhere where it can be contaminated.
Okay, next question. What are your thoughts on using brake cleaner to clean the dye?
Never tried it, but if it's a solvent and it doesn't contain any residual compounds, I would think brake cleaner is probably, I mean, just from thinking about it, quite a smart one, because the last thing you want to do is leave a residual oil layer on your brakes. So I imagine brake cleaner will probably not leave any residual oil, but I have no idea what the chemical makeup of brake cleaner is.
Okay, is there an acceptable masking agent that can be used on areas of the dye that should not be nitrided?
We tried this. This was something that was put to me about 15 years ago as a good idea on hollow dyes, that we would mask out the bridges. And we went through a quite significant list of agents from all sorts of colors through red, blue, green, brown that were painted onto the webs. And we really had a spectacular lack of success in finding anything that really had a positive effect. We found that if a dye had already got a little bit of a crack in it, the masking agent often went down inside the crack and caused more trouble than it was worth. And in general, it didn't seem to help with the life of the dyes. So I can't say there is not something out there, but all I can say is that the 3 or 4 that we tried back in 98, 99 in Holland, Michigan, we didn't find anything that worked. And I'm yet to find something that's reliable and works. But I'm open. Someone out there finds one, I would like to learn.
Okay, anybody else have questions? Remember, you can always reach out to Richard or Paul directly. And I want to remind you that today's presentation has been recorded and will be available soon on the AEC library. And to learn more about dye-related topics, watch our webinar schedule. And most importantly, watch for registration to open later in the year for the Dye Performance Improvement Clinic, which is scheduled for October 28th and 29th at the Sheraton City Center in Indianapolis, Indiana. We'll also be sending out an evaluation survey shortly, and we ask that you please share your comments with us as we depend on your input to develop future webinars. Also, as Richard and Paul reminded us, don't forget to register for the AEC Press Maintenance Workshop being held April 20th through the 22nd in Atlanta, Georgia. And visit aecmeets.org regularly to find details on these and upcoming webinars. Stay tuned for information on the next AEC webinar scheduled for April 29th, when Alcoa and Axo Nobel will present a webinar on corrosion standards. Okay, no more questions have come in. So I'd like to thank everyone for joining us today. Thank you, Richard, and I know Paul's gone, but I'd like to thank him as well for sharing all of their expert knowledge with us today. And I am Lisa Jersenko, signing off for today. Thank you all.